Okay. Thanks for invite. Sorry for taking up this time. And thanks to Mark for setting up the theoretical framework of what I want to talk about. And this is going to be about using short-range entanglement assistance for creating the resource states, which are basically remote entangled states that a quantum network is supposed to supply for further quantum information processing. So for things like teleportation or superdense coding, the network is supposed to provide high fidelity, high quality entangled states between any two network nodes as a resource. So the question is, can we make this process more efficient using short-range entanglement assistance, which I will explain in a bit. So the outline is that I'll describe what a quantum network is and some of the uses they can be put to, and how entanglement is actually distributed in quantum networks, so repeaters, and what are the rate bottlenecks for such repeaters. I'll describe what entanglement catalysis is, which is a particular form of entanglement assistance, short-range entanglement assistance. And then I'll describe how one can use that entanglement transformation for networking. Quantum network is a system of separated quantum systems, spatially separated in the typical case, which can share classical and quantum, which can exchange classical and quantum information. And the idea is that one can perform local coherent operations on up to all the qubits at any one node, but not coherent operations on qubits that lie on distant nodes. So the operational paradigm of local operations and classical communications. And in the ideal case, the quantum network allows you to send arbitrary superposition states noiselessly between any two network nodes. So this is a generalization of the classical network task where one would want uncorrupted classical data to be transferred between any two nodes. Here, we want an arbitrary superposition state to be transferred between any two nodes. As I said, the network provides entangled states as a resource for quantum information processing. But of course, being a quantum network, it has to abide by certain restrictions that we now know from the principles of quantum information processing. The first being that we are not allowed to amplify attenuated quantum signals. And so this means that we need special ways of handling attenuation. And the second thing is, of course, you cannot broadcast any information from one node to multiple nodes in the network. So how does one construct a quantum network? A variety of choices. For example, you can have discrete degrees of freedom for the flying qubits, or you can have continuous degrees of freedom. There is a choice of the physical channels which connect the different nodes, fiber optic or free space. And in case of really short range quantum networks, you can have cavity modes acting as a physical channels. And the stationary qubits at these local nodes can also be from among a variety of quantum systems or systems which can harbor a quantum state. And then, of course, there are entanglement sources. We need interfacing between the different components of the network. We need a frequency conversion, for example, to convert the photons into the telecom band so that they travel well in the physical channels. And we need detectors to tell us when indeed entanglement has been established, and so on. So, of course, we know that the most well-known use of a quantum network might be for entanglement-based quantum key distribution. And in terms of scale, this is the largest experiment I'm aware of, which essentially distributes a pure entangled state or close to a pure entangled state between 2 points which are separated by upwards of 1,000 kilometers. And the state is then verified to have a good quality of entanglement, using which a finite key rate uh, uh, of uh, of less than a bit per second is established, but even that is uh, an achievement. Uh, so if the network provides access to an entangled state as a resource, beyond QKD, one can also use this resource state to, for example, teleport the quantum information from one node to the other, specifically in the case where, for example, one of the nodes is a telescope, and we teleport the quantum information of the arriving photon at one of the telescopes to another node, so that we effectively create an entanglement-enabled aperture that can actually increase or maintain the signal to noise ratio while going to larger baseline sizes, baseline being the separation between the two telescopes. And so in some sense, this is a complementary way to improve the results of the very first talk today, which talked about hypothesis testing. But in this case, by using an entangled resource state between two telescopes, one can circumvent the problem of photon loss of the signal photons by actually not needing to physically transport the photons from one telescope to the other, but transmitting the quantum information of the arriving photon using teleportation. That's another use. And then there are more applications. For example, one can use an entangled network state to create a network of clocks with a much higher precision than would be possible by using these clocks separately, each of which are quantum clocks, but taken together and using an entangled network state, they can give us a much higher precision of their timekeeping. And then one can use these resource states provided by the network for more fundamental uses, such as tests of Bell inequalities. So I told you what the resource states may be useful for, but how are these resource states created? So in a network, if you imagine these dots being the network nodes, once we identify the nodes between which I need an entangled state, so for example, A and E here, the way to create entanglement between A and E is actually to forego a direct generation of entanglement, because that turns out to be very lossy. And the rate in that case, the rate of establishing any entangled state between the two remote nodes would go down exponentially with the total channel length. So repeaters are a way where you identify a one-dimensional sequence of segments in the network. So you divide the entire length into multiple small pieces, and if you do it up to a reasonable number of times, it's possible that the rate, instead of falling off exponentially with the total distance, will fall off exponentially with the segment distance. And this segment distance, because you control, the raw rate could be brought down to scale inversely polynomially with the total distance as compared to exponentially with the total distance. So in this process of distributing entanglement between A and E, there are three basic steps involved. And the first is the entanglement generation, which essentially creates short-range entanglement between, let's say, between neighboring nodes. The entanglement is generated independently over all the network nodes and asynchronously over all the segments and asynchronously. But of course, uh, the generated entanglement typically is not in the form of perfect Bell states. So there is a loss of entanglement quality even as they are generated, even as the states are generated. So we need some form of purification before the entangled states on adjacent segments are connected using entanglement swapping, for example, because connections in general lead to an average reduction of the entanglement quality. So if you imagine many such connections over a long range repeater, then the entanglement quality between the two furthest nodes is severely reduced. So one needs purification in order to pump up the entanglement quality over each segment before the segments are connected, and you can have a reasonably good entanglement between the two remote nodes. And so the goal of any entanglement distribution protocol would be to maximize this product of the rate at which one is able to establish remote entangled states, rho AE, and the quality, the entanglement quality of these states. Here, for example, quantified by the concurrence of the state AE, rho AE. And so this process of one-dimensional entanglement distribution has certain issues, and the bottlenecks to this, to the rate, to the effective rate, are of two kinds. One is the loss error, and the repeater philosophy of dividing and conquering the total distance while mitigating the loss error actually also gives rise to a lot of operation errors. And the reason is that because the repeaters, the efficiency of repeaters is based on the fact that the successful entanglement generation over any segment allows you to wait for the unsuccessful segments to generate and be successful in their entanglement generation attempt. So there are errors while you wait, for example, because of the degradation of quantum memories which store your entangled state. There are errors arising due to the fact that the operations you may implement will not be perfect. And there are also errors because due to transmission in the fiber optic channels, for example. And as I said, the short range entanglement over each segment has to be of a sufficiently high fidelity for the entanglement quality between the two remote nodes to be of a reasonable value. And in the pure state case, when all of these segments are generating pure or close to pure entangled states, the final entanglement, the final average entanglement as an outcome of the entanglement connections made at all the intermediate nodes turns out to be a product of the concurrences of the states on each segment. And this is the best case scenario, and actually this product serves as an upper bound for the case of mixed states. So in general, the average concurrence is typically much lower than the product of these, the individual concurrences. And so one needs to purify the entanglement over each segment, which is an iterative procedure, and which was talked about and entanglement in the previous talk, purification or distillation, where I'm given multiple copies of the initial state rho AB, for example, and I would like to perform LOCC operations. So if the state is between A and B, I'm allowed to perform local quantum operations at A and separately local quantum operations at B. And we can coordinate the actions using classical communication with the end goal of arriving at a final state, which has a higher fidelity value and also concurrence value. So fidelity and concurrence are proportional. They are proportional for pure states, but they follow the same trend. So a state with a higher fidelity also has a higher concurrence, even for mixed states. And so one wants to push this fidelity or the concurrence value higher in an iterative process where if I'm given two copies of the state rho AB, then every single time I perform the purification process, I gain a slight bump in the resulting fidelity of the output state. But this happens probabilistically. And so asymptotically, once I do it enough number of times, I may be able to reach a very high fidelity value, which is sort of essential when you want to distribute entanglement over very long distances. So let me just check the time. Okay. So one problem with this is that even though this linear chain is part of a network, quantum network, it doesn't really use the network structure, and it uses only LOCC operations, and it reaches high fidelity only asymptotically after a large number of iterative operations. So using catalysis, there is a way in which, in addition to the entanglement resources along the primary path, so I would call the yellow highlighted path here the primary path, we can use the entanglement resources generated on the auxiliary paths of the network in order to enhance the entanglement distribution rate between A and E. And so what this approach does is that it will utilize the entangled states that are provided by the auxiliary paths to increase the efficiency of single shot entanglement transformations along the primary entanglement distribution path. And so this mitigates the operation error for a specific model, and it's resource efficient in terms of primary entangled states, because all you need are at the very minimum 2 copies of the primary entangled state and a single copy of the catalyst state in order to effect that single shot purification. The end goal here, this is not an iterative process, it's a single shot process which succeeds with some probability. And if it does succeed, then the final state turns out to be a pure Bell state. And so this entanglement distribution based on catalysis uses something called catalytic entanglement concentration, and this is a entanglement transformation procedure that goes beyond the standard LOCC paradigm. Here, E standing for entanglement assistance or entanglement assisted LOCC, where we obtain entanglement assistance in the form of a catalyst state. And so what this does is that if my success probability of transforming between psi and psi tilde using just LOCC turns out to be is Pmax, then by attaching a catalyst state, which I can recover at the end of the process, I may be able to increase the success probability of this transformation. And so we can utilize this for the case of the network edge entanglement transformation, where we have certain number of copies of the primary entangled state and a catalyst supplied by the auxiliary green paths, ending up with a pure Bell state and no entanglement elsewhere, and the catalyst state, so that we can reuse this catalyst state whenever the previous transformation has succeeded. So this is just a pictorial description of what I said. We have, for example, a certain number of quantum memories at A and B, and the least you need are 3 quantum memories on each of the nodes. And we have the primary entangled states psi, n copies of psi, along with 1 copy of the catalyst. And these psis are partially entangled, so they are not, so they have fidelity less than 1 compared to a pure Bell state. And after the entanglement assisted procedure, catalytic procedure, we may have 1 maximally entangled state, and the others being states of zero entanglement, and we retrieve the catalyst back. So a use case for this, for example, could be when we have heralded quantum memories and polarization dependent loss in the fiber optic channels. So even though the source produces, let's say, very high purity belt states, because of the polarization dependent loss, what the quantum memories receive are really distorted entangled states. And here, the alpha parameter, the closer it is to 1/2, the more entangled the state, the primary entangled state psi is, and the closer it is to 1, the less entangled it is. So if I just perform and the process of entanglement concentration, which is when the one of the final states is a belt state, with just 2 copies of the primary state and the optimal catalyst. So the catalyst also depends on the initial state, on the primary entangled state. Then if I do this with 2 copies on the optimal catalyst state, what this plot shows you is that with catalysis, one has a much higher success probability of the transformation for a range of alpha values, and particularly when alpha is close to 1. So for very highly distorted initial states or highly distorted primary entangled states, the catalytic procedure can give a good bump to the success probability of this entanglement concentration procedure. And this plot just compares it with other possible LOCC methods, and it goes to show that even for the optimal LOCC process, which is this straight line, the catalytic process performs much better. And so, because we're talking about entanglement distribution, one needs to keep in mind the resource requirements, and what the catalytic procedure needs is a quantum circuit at each of the nodes, which can implement this catalytic procedure. And the circuit depth for this minimal example turns out to be about 100 in terms of the basic gates. We also need to keep in mind the temporal cost of achieving these entanglement transformations over each edge, because if the expected value of if the expected temporal cost over each elementary segment is known, then one can essentially calculate the total time to distribute long-range entanglement by multiplying this temporal cost over each segment by the waiting time over all the network edges. The waiting time being the expected number of attempts after which all the segments will have a belt state for entanglement connections to work at the intermediate nodes. And so it turns out that the temporal cost of performing this entanglement transformation, catalytic transformation, when multiple auxiliary paths are available between A and B. So in addition to the primary, sorry, this should be yellow, and there are multiple green auxiliary paths available, then it turns out that essentially one can ignore the cost of generating the catalyst states between the between the neighboring nodes. So in some sense, you get the catalyst states temporarily free. They're always available when you need them to be. And so this is the case when many auxiliary paths are available, that one gets the maximum advantage in terms of entanglement generation rates. And as one can expect, when there are no auxiliary paths available, it's just a linear 1D chain, then this advantage vanishes. And so to show that, one can plot this ratio of the entanglement distribution rate over, in this case, 32 network edges, using catalysis to using the optimal LOCC. And we see that as the states get more corrupted because of the polarization dependent loss, so alpha tending to 1, one gets up to an order of magnitude improvement in the entanglement distribution rate. And this also depends on the nature of the catalyst used. So a higher dimension catalyst makes this process of entanglement transformation, which is the entanglement concentration process, more efficient. And so this gives a slightly higher gain of the entanglement distribution rate as compared to a catalyst of smaller dimension. And so what this approach of distributing entanglement does is we were able to aggregate the entanglement resources of the auxiliary paths along with that of the primary entanglement distribution path in a much different way than is typically used in quantum repeaters, which only rely on LOCC transformations. So, of course, I showed this to you for a specific model, but in order to be more relevant for quantum networking, this needs to be generalized for other quantum channels. And related to this is also the question that these catalytic transformations actually rely on us knowing the precise form of the corrupted primary entangled state. But in case that is not known, or we only know a possible distribution of corrupted states, so again a different kind of channel, then can we have catalytic transformations which increase the efficiency of a one-shot like procedure? So essentially obviating the need for the iterative purification procedure, which is very, very resource intensive. And then, of course, what kind of quantum network topologies can utilize catalytic transformation efficiently to distribute entanglement faster? And so I'll conclude by saying that I gave you an example of catalytic entanglement concentration over network edges that can significantly boost the entanglement distribution rate. And it's resource efficient because in the simplest case, it requires only 2 primary entangled states and a single 2x2 catalyst state. And it's a one-shot procedure, so not iterative as the distillation or purification, but we saw that it needs prior state information and it needs to be widened. It needs to be made applicable to a wider class of quantum channels. So that's it. Thank you for listening.
All right. Thank you, Sid. Does anyone have, we have a few minutes for questions, or many minutes, or depending, if anyone wants to ask Sid a question, jump right in.
Right. Thanks for your talk. So did you look at catalysis with mixed states at all?
So I think Eisert has a paper, Jens
Eisert, okay.
Yeah. They have a paper with mixed states, and maybe I do not understand the paper completely, but what it says is that at least for purification in the standard way, catalysis does not work.
For any mixed state?
That is my understanding.
Oh, okay. I don't know the result, but somehow I'm like skeptical. It seems like if you have a mixed state, you can still do something useful with catalysis. Anyway, it's an interesting idea, what you were talking about, to use catalysis in a network. I hadn't seen that before. I had seen the theory papers on catalysis, but that's a nice way that it can come about.
Did anyone have anything else?
Yeah, just quick one in the page 13. You talked about the polarization dependent loss,
Mhm.
and it seems like another loss, but rotation. But why do you call it that way?
Why do I? So
Yeah, you have a bare state, and then
Yeah.
memory gets the pure
Right.
state, even if this is loss.
Right. Right. So yeah. So the so my understanding is that this distortion from a pure Bell state to this final imperfectly entangled state comes about because the two polarization modes have different losses in the optical channels, and the net state that you can describe at the end is the state psi.
Yeah, but it is pure state again. Yeah, even with the loss, and then
You're saying you would not
Yeah.
call this loss, you would call this something else?
yeah, I would expect something like a mixed state. Yeah, HV and pH mixed state with
Mhm.
some unbalanced probability. But this one seems like just a rotation, isn't it?
What is the loss you're talking about? I think you're talking of entanglement loss, right? You had perfect entanglement before, and now if you have less entanglement, it's still a pure state. Could that be?
Yeah, it is a loss. It is definitely a loss of entanglement.
Right.
My understanding is that one of the two modes, the fiber optic channel provides more loss to one of the two modes
Right.
of the pure state, and so there is a loss of the entanglement quality, for sure. But I think Professor Lee says that that should result in a mixed state and not just a pure state. But my understanding is that this mode of loss can also can lead to this final pure state.
Yeah, because if this is the state, the end of the final state, then you could have like say like you flip H and V,
Yeah.
and like pass through the same path again,
Right.
and you will recover the
Absolutely.
initial state. Yeah.
Absolutely. So that's a method called filtration, or the filtration method is inspired by that, and it's essentially if I know the form of the state psi, that is how corrupted it is, and then I can basically I can compensate for the loss in one of the polarization modes in the other mode, and basically balance these coefficients in order to bring it to a maximally entangled form. And the easy thing about that LOCC, purely LOCC based method, is that it will work on single copies. So all you need are just one copy of psi and filter. But as we see here that there are better methods available than filtration even for LOCC, and catalysis definitely does better than that. Of course, the cost to pay is the much larger complexity of performing the catalytic transformations.
Okay, not quite satisfactory, but yeah, fine. Okay. Yeah, because the conjugate process would be amplification if this is called loss. Yeah? Okay.
All right, are there any other questions? We can maybe stop it there.